Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 30th, 2026, just 3 days ago. It introduces a pipeline called Golden Goose that transforms reasoning-rich but unverifiable text, like textbooks or web scrapes, into verifiable multiple-choice tasks, allowing models to break through performance plateaus where they previously stopped learning. The paper is titled Golden Goose, a simple trick to synthesize unlimited RLVR tasks from unverifiable internet text. And as we'll see later, the results are really impressive, showing that this synthetic data can help generalist models outperform larger, domain-specialized systems. Figure 1 illustrates the Golden Goose pipeline, showing how raw text becomes a verifiable training task. At the top, we see inputs like web scrapes, STEM textbooks, or coding problems that lack test cases. In the middle layer, a large language model processes this text by identifying a key reasoning step, replacing it with a mask token, and creating plausible distractor options. The bottom section shows the result, a standardized multiple-choice question. This cleverly transforms open-ended material into a format where the correct answer is just the original text, making validation automatic. So, Figure 2 tests if this synthetic data actually helps after the model, QN4B instruct, hits a learning plateau. The purple line shows the standard Pro-RL dataset, where the model flatlines or regresses across all three domains. However, the green line reveals the impact of adding the new Goose reason data. In the math panel on the left, performance breaks out of that slump and climbs steadily, and we see the same revival in the code and STEM panels. Figure 4 investigates a crucial design question. Should the synthesized tasks be open-ended or multiple choice? The chart tracks model success rates, where red indicates 0 correct answers and green represents consistent success. The top bar shows the open-ended format, which is almost entirely red because the model often ignores the fill-in constraint, providing no useful learning signal. Conversely, the bottom bar uses just 3 choices, which turns out to be too easy, shown by the dominance of green. The authors settled on the 9-choice format in the second row, which creates a balanced medium difficulty regime that is ideal for reinforcement learning. Well, Figure 3 quantifies exactly how much more signal this method provides compared to standard datasets. Here, the authors distinguish between total examples and effective examples, which are tasks where the model doesn't just pass or fail every time, but actually struggles enough to learn. Looking at the top section in purple, representing the standard Pro-RL blend, we see fairly short bars, where only about 20 to 30% of the data is actually effective. By comparison, the green bars at the bottom show the new Goose Reason dataset. These are not only massive in total volume, but they also maintain a much higher effectiveness rate of around 70%, creating a 13-fold increase in useful training data. Alright, having established that the signal is cleaner, Table 1 shows how this translates to actual math scores on benchmarks like AM and math. The first block tracks the QN4B instruct model. If you look at the rows for the Pro-RL dataset, performance peaks around step 333 with an average of roughly 72%, but then regresses as training continues. However, the row labeled plus Goose Reason shows that adding the synthetic data reverses this slump, boosting the average to nearly 74%. This gain is substantial enough that the small 4B model starts closing the gap with the much larger 30B reference model listed at the bottom. So, having proven the method on math, Table 4 takes a bold step into cybersecurity, a field with almost no verifiable training data. Here, the authors compare their 4 billion parameter model against Llama Primus, an 8 billion parameter model explicitly specialized for this domain. Looking at the top rows, those specialized Llama Primus models achieve an average score of roughly 68%. However, the bottom row shows that training the smaller generalist model on Goose Reason cyber data boosts its average to nearly 79%. This is a massive 10-point lead, proving that synthetic tasks from raw text can outperform expensive, domain-specific pre-training. Wrapping up, 2 takeaways stand out. Golden Goose solves the data bottleneck in reinforcement learning by successfully converting raw text into verifiable training tasks. This suggests we can now train powerful reasoning models in specialized fields like law or medicine, where verifiable data is scarce, simply by using existing literature. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.